Hello! I always start these videos off with okay, so I thought I'd start with hello. Alright, this is our first Chapter 9 lecture. Going to be two of these, so I'll put this in the corner. Call this Lecture 1. So hopefully you got a printout of your notes. Let me know if you have trouble printing out these Word documents. I'll put them up from now on as a PDF if that works better. Just message me in Microsoft Teams for that. All right, so this chapter is about momentum. So the momentum equation that you need to put in that blank spot, we use a small p, and it is a vector, so we put that little half arrow, and it's equal to mass times velocity. So this is an equation you'll use a lot. The unit is a kilogram meter per second. That should make sense. Mass in kilograms, velocity in meters a second. All right, it doesn't really have, it's not named after a person, like a watt or something from last chapter. Okay, so momentum, the direction is always the same as the velocity direction. So objects with the same mass traveling at the same speed but in different directions will have different momentum values. And Newton referred to momentum as a quantity of motion. So just like so much of what we do, it all kind of reverts back to Isaac Newton. Excuse me. So let's look at 9.1. That in your field of view. So it says a 35 Newton rock rolls down a hill. At the bottom of a hill, it's rolling horizontally with a velocity of negative 13.2 meters per second. What is its momentum at that point? Okay, so this is just going to be a problem where we get used to using the equation. All right, so we do need to get the mass, and that's going to be 35 newtons over 9.8 meters per second squared. That's 3.57 kilograms. All right, so now we can calculate the momentum. It's mass times velocity. So that's 3.57 kilograms times the velocity of negative 13.2. I think the author wanted to give you one with a negative in the beginning just to show you how momentum can have a negative value. So negative 47.14 kilogram meters per second. All right, let's go back to the notes. Impulse, all right, so this is the topic that we're going to talk about for several on your own problems. The change in momentum. All right, so the impulse equation that we're going to be using is the change in momentum is equal to the force, of course that's a vector, times the change in time. All right, another way of writing impulse is the change in momentum is equal to the final momentum. All right, we'll do F, piece of F from now on, minus the initial momentum. Okay, so we'll be using both of those equations. So the derivation in college, a lot of time is just spent deriving formulas, all right, and not nearly enough time working problems. But I wanted to go ahead and give you an example of how did this impulse formula come about. So if we start with F is equal to ma, right? We use that a lot in Chapter 5 and Chapter 6. We can rewrite that as force is equal to mass, and then acceleration is the change in velocity over the change in time. Remember that all the way back to chapter 1. Okay, and that we can say force is equal to mass times final velocity minus the initial velocity over the change in time. So then we can write that, okay, we're just keep coming from there, as the force is equal to mass times the final velocity. Let's distribute that mass minus the mass times the initial velocity over the change in time. Okay, well, what is mass times velocity? Well, we just learned that's momentum. So force is equal to the final momentum minus the initial momentum over the change in time. And that is just the force is equal to final minus initial momentum. That's just the change in momentum. Okay, and if you rewrite that, you'll come up to here, right? Solve for change in momentum, and and you'll get this right here. So interestingly, Isaac Newton started out with this and worked backwards to get to F equal ma. Even though F equal ma is a more famous equation, his work started out here, and he went backwards to get to F equals ma. So I thought that was pretty interesting. All right, pause the video if you need to. Okay, let's talk through the notes a little more. So a few impulse examples. So let's think of a ping pong ball versus a golf ball. All right, you know that a ping pong ball kind of is, the skin on it is pretty weak. So if you were to throw it hard enough, it would crumple some. All right, whereas a golf ball is really hard. Okay, so that's why you could throw a ping pong ball at a much faster velocity. Even let's say you could throw a ping pong ball with the same momentum as a golf ball. Of course, you'd be throwing the ping pong ball faster, but the force would be less because the ping pong ball, since it crumples, would spend more time. Let's say somebody would throw it at your noggin. It'd spend more time on your noggin, and so that would make the force be less than a golf ball, which is really hard and bounce right off. So with our egg drop, if those of you who made a really bouncy straw structure, the structure spent more time in contact with the ground, right? It kind of bounced or bended as it hit, right? So that causes that more time it spent on the ground reduce the amount of force, right? Because impulse is force times time. It increased the time, reduced the force. So that's those of you who survived, that is the reason it survived. All right, or at least one of them if it did. Newton's third law, how can the force be reduced? By increasing time of impact. So that's what I was just talking about. Another thing is, let's say with tennis, the follow through, okay? If you don't follow through, if you stop as soon as the racket hits the ball, you're going to have to give a lot more force to get the same momentum than if you follow through and the racket spends more time on the ball. The same thing would be true of kicking a soccer ball. If you chose not to follow through with the swing of your leg, then you're not going to have much time against the ball, so you'd have to kick it with much greater force. All right. Okay, let's turn over to the next page. And we will work 9.2 and 9.3. So let's go ahead and rewrite our impulse equation. And also delta P is equal to final minus initial. Okay, looking at 9.2 on page 294. Okay, so it says a baseball, mass 145 grams, thrown by a pitching machine is clocked by radar with the speed of 45 meters a second. If the roller wheels of the pitching machine exert 43 newtons of force on the baseball as it's launched, how long did the baseball stay in contact with him? So anytime in this chapter when you hear a how long, if time is involved, you know it's going to be an impulse problem. Okay, so we know that the change in momentum or impulse is equal to the force times the change in time. We are solving for change in time, so that's going to be the change in momentum over the force. All right, so that is going to be, change in momentum we know is the final momentum minus the initial momentum over the force. All right, and so that's going to be the mass times the final velocity minus mass times the initial velocity. Oops. Over the force. Okay, so now we can plug our numbers in. So our final velocity, all right, the final velocity is, we're going to have a final velocity, but do we have an initial velocity? Okay, well, the baseball is just sitting in the pitching machine, so we don't have an initial velocity. So it's going to be mass times final velocity over the force. Okay, so now we've got 0.145 kilograms, excuse me. Final velocity of this thing is 45 meters a second. And the force, which would be the hardest thing to know in this problem, is 43 newtons. So that's 0.152 seconds. All right, so you wouldn't expect the baseball to be in the pitching machine for very long. All right, so that kind of makes sense. Okay, let's see if I can fit 9.3 in here. I got to start taking some genius scans of these problems so I'm not have to pull this big book over. So, tennis ball travels with a horizontal velocity of 23.1 meters a second. Tennis player takes her racket, hits the ball, returning it with a horizontal velocity of negative 29.7 meters a second. If the ball and racket are in contact for 0.21 seconds, how much force did the tennis player exert? All right, so using the momentum equation, change in momentum is equal to the force times the change in time. This time we want to know the force. So that's going to be the change in momentum over the change in time. Okay, that's going to be the final momentum minus the initial momentum over the change in time. And so that's going to be the mass times the final velocity minus the mass times the initial velocity. Did it again, dadgummit. Over the change in time. Okay, so let's see what we can do here. The force is equal to, the mass is 0.0567 kilograms. The final velocity is negative 29.7. Then we have 0.0567 again. The initial velocity, all right, is 23.1 meters a second. Ooh, that makes for a big numerator, doesn't it? All over, you could do these separately if you want and then put the numbers in the formula. And that's all over 0.21 seconds. And you will get minus 14.3 newtons. It's okay that it's negative. All right, it just means that the force is going in the negative direction, okay, because the ball is returned in the negative direction. So that does make sense there. Okay, pause the video if you need to. I'm going to erase this and we will finish up the lecture momentarily. All right, on your notes, we're talking about we're going to not work any math problems until tomorrow, but the law of momentum conservation is the net external force acting on a system of objects is zero. Excuse me, let me read that again. If the net external force acting on a system of objects is zero, the total momentum is conserved. Okay, so what does that mean? Momentum conservation. It means momentum before is equal to momentum after. Okay, so I've already given the tennis example. Let me give you a different example. Let's call this a gun example. Examples of momentum being conserved. So, man, I'm a terrible artist. So let me try to draw a rifle. All right, I've seen worse. Let's say you were able to suspend this rifle to the ceiling. Nothing was touching it. It was just suspended to the ceiling with a couple of cords. And let's say that it's loaded, you were to pull the trigger, and so the bullet, right, would go out that way. What is going to happen to the gun? If you've ever shot a gun, what does it do against your shoulder? Well, it recoils, right? But your shoulder stops it. In this case, okay, we're suspending it from the ceiling, so the bullet goes to the right, the gun is going to go to the left. Okay, so there are no external forces acting on this like your shoulder would be there. So in this case, momentum is conserved. Now the next example is the ice skater example. I don't know if any of you have ever watched any ice skating, but what they do is they'll do something called, well, let's think about it this way. Okay, let's say you have a man and a woman ice skater. It's one of the team things. And the man is just standing there, and the woman goes toward him in the ice skates and jumps up into his arms. Okay, he's going to move in the direction that she was moving, okay, because there's no external force. He's not up against the wall. And I'm not going to try to draw ice skaters here. So he's not up against the wall. So in that case, momentum would be conserved. Okay, let's look at 9.4. Now, it's not going to be a big deal to you because when we do math problems, momentum conservation will always apply. So an astronaut is floating in space near a ship. He has a ball in his hands and is essentially motionless. He suddenly throws the ball because all astronauts take a ball out into space. Such a great example. Does the law of momentum conservation apply to the astronaut and the ball? Why or why not? Okay, so for 9.4, the answer is yes. No forces outside the system so that is the ball / astronaut do you spell astronaut? Guess I can look at the book. Holy Toledo. A-U-T. All right, no forces outside of the system are acting. Seems kind of redundant, sorry. All right, there's no force, outside forces. So what that means is the astronaut, that's not how you do it, will recoil. He'll go the opposite direction of the ball. All right, 9.5 says, a toy car is rolling along a floor. It suddenly crashes into the wall, coming to a complete halt. Does the law of momentum conservation apply to the car and the wall? Okay, the answer there is no. The wall is attached to the structure. You know, if it were a wall on wheels, you know, like that big whiteboard in the gym that's on wheels, then, you know, there would be momentum conservation would certainly more apply. There's still some friction involved, but a wall is attached to the foundation, right? And that's an external force. So momentum conservation doesn't apply. Okay. So the homework that goes with this section is review questions 1 through 7 and practice problems 1 through 4. So I hope you have a good rest of your day, and I will talk to you next video.